One of the things that engineers soon learn is that no project is ever really finished. And part of the engineering process is deciding when an enhancement would be indicated or when it's better to just wrap everything up and get it off to production. So I have reached kind of that point on this project. However, I have decided that there is a better way to do this than the one I had intended. And so what I have done is redrawn the schematic. Let me explain what I see wrong with this system. With this system, the 80 megahertz and the divided down 40 megahertz will both be running all the time, whether you're using them or not. In other words, even when you're using the thing in the direct mode, these are still running. Those might interfere with whatever signal you're looking at. Further, when the 80 is running, and you're using the 80, you probably don't want the 40 around because it's producing harmonics that can get into the spectrum. So what I have decided to do is to not use the flip-flop, instead to use a separate 40 megahertz oscillator and to use a double pole switch so that I can not only switch the output, but I can also switch the power to these oscillators so that only one of them is running at a time. So if you're using the 80, you don't have a 40 megahertz square wave floating around inside the unit. I also have decided, since I drew this schematic, to do a similar thing with the switch over here, so that in addition to having a direct through, if I use a double pole switch here, what I can do is when it's in the pass-through position or the direct position, I can shut off all the power to both oscillators. So in other words, this VCC, instead of going directly to 5 volts, will go through another switch that has a pole on this switch. So in other words, so that they move together. So that when you switch this switch to the direct position, it disconnects VCC from this point. So let me get on with that and start working on the actual prototype, in the hope that I can perhaps pass on some techniques that other people have taught me over the years for assembling RF devices. And this, of course, is an RF device since it operates above a megahertz. The BNC connectors, when they are mounted to the box that they're going to be mounted in, you have to make 2 connections. With coax. One is the braid of the coax, which is what you might call the ground or the shield, and the other is the center conductor. Now what I like to do is, if you notice, there is a ring that is fitted on here that comes out to a tab with a hole in it. And that is what I have up here. You may notice I have stripped the coax and twisted the braid to make a connection, and then run that braid through that little hole in that ring. Now I usually do all of this before I try to mount the BNC connector in the cabinet. Now in this case I'll be drilling holes in each end. And once again, it's a little thing you need to think about ahead of time, is how you're going to assemble this unit. I'm going to install the BNC connectors in each end, and then the switches on the top there. And the reason that I'm doing that is that will allow me then to put the board in like this, make the connections to the BNC connectors on the end and to the switches underneath, and do all of that before I try to mount the board in so that I can get to the switches and so on. Also, it makes it easier later if I want to test if I mount the board this way with appropriate markings on the bottom so that I can get to test points. Like you see this oscillator I just have set in right now, and I'm holding it with my finger. But later there will be solder connections there, and I will mark those with pin numbers so that I can find the particular test points if I need to test it. Now, you might ask why I used that side of the box instead of this side of the box. If I were putting the BNC connectors on the sides of the box instead of on the ends, then I would have mounted everything in this piece. They're usually, the U, if you will, of the metal is one piece has the ends as part of the U, and the other piece has the sides as part of the U. So just think about that before you start trying to drill holes and mount parts and so on. The reason that I like to solder these tabs on first, these grounding tabs, is I have found it's difficult to get the tab on the, or to solder to the tab on the BNC connector at the same time that you're trying to make the connection to the center conductor. And the reason is that this cable is fairly stiff. So I hope those tips will help people working with coax cable in an RF environment like this and BNC connectors. Here is the completed unit in the box that I said that I was going to put it in. On the left, of course, is the BNC in, and the BNC out is on the other end. Of course, it has two positions for this switch. One is the passive and the other is the converter or active side. 80 and 40 megahertz switches there. So that basically you can either pass the signal through the box or you can convert it with a 40 megahertz input to the mixer or an 80 megahertz. Now you've already seen the performance of the box or of the circuit with the analog discovery. I did want to point out I made one additional change to the circuitry, and here is sort of the final circuitry. I inserted a 0.1 mic capacitor in the input, in the RF input to the mixer, and I did that in the unlikely chance that someone might connect a DC source to this input. That blocks the DC from coming into the mixer. That's done in large part just to protect the mixer and or the DC source, because the input to this mixer is a very low resistance transformer winding, and if you put quite a bit of voltage on here, a DC voltage on here, you could either blow the mixer or you could draw too much current from the device. So that's just more protection than anything else. But there is one last test that I did want to perform on the box, and that was to see what its effect was on frequency response. That is, if you pass a signal through this box, how much does the box affect the frequency response of the signal? And in order to do that, I'm going to use a spectrum analyzer, and so up here I have set up a DSA 815, and I'm going to be using the tracking generator. First, what I'm going to do is set the tracking generator to work just with a pass-through. Once I have determined that this is flat in a pass-through case, then I'm going to connect it to the box and see how much the box affects the frequency response. So let's do what What I'm going to first do is turn on the tracking generator. And there you see we have the tracking generator on. Then I am going to normalize. And I have the reference level set to 10 dB instead of 0, just so it moves it down a little bit. You can see it perhaps a little bit better. Let me zoom in now a little on the screen. And now let me connect it without changing the spectrum analyzer. I'm attaching the input and the output. Now, what I'm doing is I'm using a 500 megahertz span, a stop frequency of 500. In other words, a center frequency of 250. Now, the part that I'm really interested in is the part up to the time where we could do conversions. But these ripples indicate that as you get out around 200 megahertz or so, you start seeing ripples in the passband. They're not really bad. They're probably about 2 or 3 dB. But nonetheless, that means that measurements made out here will vary by the 2 or 3 dB that you see on the scope. Now what I'm going to do is I'm going to change the stop frequency to 120 megahertz, which is the stop band, or the highest frequency that this unit will effectively convert. And there you see we're pretty flat out to 120 megahertz. So I'm quite satisfied with the performance of this of the box. Part of the reason for doing this test is construction technique has a lot to do with how with the frequency response. And one reason that I used coax cable inside the box, even though it's just such a short distance, was to try to preserve the 50 ohm integrity of the system as much as I could within the range of something that a prototype that is hand constructed like this. So once again, I'm happy with the performance of the box. The circuit does seem to do what it's intended to do, and I think this will be a useful addition to an analog discovery lab. So if you would like to build one of these, I'll leave this schematic on the screen for a little bit as I sort of wrap up what we have done. The basic analog discovery only goes out to about 50 megahertz in the spectrum analyzer. And what we have now done is, by using a mini circuits mixer and a couple of crystal oscillators, extended that frequency coverage out to about 120 megahertz, or perhaps 130 megahertz at its top end. Now, there are some things you could do differently. If, for example, you want a little better frequency resolution, you could change one or both of these crystal oscillators. You could just build it for one if you wanted just to go out to about 90 megahertz, in other words, a range of 40 to 90. And so there's a lot of different possibilities. I would not recommend trying to push this much beyond about 150 megahertz, however, because at that point, construction techniques and other things make it very, very difficult to achieve useful frequency response without seriously impacting the measurement capability. So once again, I hope you have enjoyed this series. It's run a lot longer than I expected, but it does illustrate that when you get started on a project, sometimes that's the only time that you really know how the project should have been done from the beginning. So I think that at this point, this is about as good as I'm going to get it. I could probably further refine this technique, but as I admitted in one of the earlier videos, there are other ways to probably accomplish this that might even be better than the way I've chosen. This is just a nice, inexpensive way to extend the analog discovery's frequency range. I mentioned early in this overly long series of videos, that the engineering process also consists of knowing when to stop. Unfortunately, I have, I think, far exceeded that rule. After completing the converter that I showed in part 3 and the early part here of part 4, I decided to separate the oscillators from the mixer. I did that for a couple of reasons. One was to get the oscillators out of the box that the mixers are in, so that I could shield the mixer completely. The second reason was that allows me to use other oscillators as well, including function generators and so on as the local oscillator. So what I've done is I have removed the oscillators from this, replaced them with another BNC connector that allows you to put a local oscillator signal in from the outside. I left the pass convert switch so that you can either pass the signal straight through to the analog discovery or convert it based on the local oscillator signal. So let me show you that circuit. And here it is. I also replaced the tough mixer, which had been hardwired, with a socket. The purpose is, if I later want to go to a different mixer, Mini Circuits makes a number of mixers that fit this same 4-pin socket. So by using a socket, I can change the mixer. So basically, you'll see this is exactly the same circuit I had, except without the 80 and 40 megahertz oscillators. Once again, I've run on real long on this thing, so I hope you won't mind me kind of showing you how it finally wound up. But nonetheless, I do think this is going to be a useful project. So now what I'm going to do is hook this thing up and test it under this new configuration. And for that, I'm going to be using a couple of signal generators. I'm going to put an AM signal in at a few frequencies, but I'm going to start probably with about 20 megahertz, 30 megahertz, and with maybe a 20 megahertz local oscillator to see if I can convert it down to 10 megahertz, which will then allow me to see the 20 megahertz signal and give the analog discovery in this particular case with that local oscillator a range of from 20 megahertz up to 70 megahertz. With 100 millivolts peak to peak of carrier, this is at 10 megahertz, 20 megahertz. You see the spectrum. This is the input signal at 30 megahertz. This is the local oscillator at 20 megahertz. This is the down-converted signal at 10 megahertz. What I'm doing, the reason I'm doing that is I'm trying to determine what is the optimum local oscillator level so that the level of the input translates to the level of the output. In other words, this 30 megahertz signal is converted down to 10 megahertz, but at the same dBm level. So what I've determined is that at least at 20 megahertz, that value is 100 millivolts peak to peak. Hope you have enjoyed this series, and I look forward to perhaps presenting some more videos on the analog discovery. But for now, let's move on from this topic. Have a good day.